Have you ever had this feeling of accomplishment? The feeling that you've done the work, the job, you have done it well, and you're proud of yourself. Like, let's say, last Friday, for example. You spent the past 2 days writing tests, making sure that everything works, and on Friday evening, you run the test, everything passes, and the cherry on the cake is that you even have 100% of test coverage. So you think you can go on the weekend, everything is perfect, you are happy. But then comes Monday. On Monday morning, you still remember this feeling on Friday. So you're happy, you go to work, you open your mailbox, and then you're flooded with hundreds of emails of bug reports. So what happened? What did I miss? What did I do wrong? I will go back in a brief history of debugging and test. So a long time ago, let's say you wanted to test an application, you had to do it manually. So you were just compiling your application, running it several times, trying everything you could try, and then see if it worked. It worked because you had like software with a few features, and it still works if you have very few features on your code and your application. But as application become bigger with more methods, more classes, more files, this is not reliable. You can't do it manually. So that's why people invented test framework. They came and they fixed this, finding bug experience. They fixed it, and it makes it more efficient to find bugs. You have test framework like PyTest for Python or Jest for JavaScript. But does that mean that it tests your code efficiently? So that's the question we're going to answer. Because on top of that, this framework, what they bring to you is this code coverage or test coverage. And what you may think is that if I get 100% of test coverage, that means my code is tested and everything works. So does 100% test coverage mean 100% of your code is tested? Does 100% test coverage means 100% of your code works and is efficiently tested? Well, the answer is not necessarily. 100% of test coverage means that every line of your code has been executed at some point in a test. Doesn't mean it's all good. So hi, everyone. My name is Olivier. I'm a developer advocate at AWS, and I'm very lucky to be here today with...
Hi, everyone. My name is Maha. I am an engineering manager at Elastic. I'm leading a team named the Releasing Engineering Team. We are responsible of providing framework and tooling and guidance to the other product teams at Elastic, helping them to produce releasable artifacts. I worked before that as a DevOps engineer, and I also have a PhD in optimizing performance of multi-tier distributed system deployed in the cloud. And today, I'm super excited to talk about mutation testing and how can we benefit from it, how can we implement it, how can we use it. First of all, let's answer the question, what's mutation testing? Mutation testing, it's a technique can be used to evaluate the efficiency, the effectiveness of our test suite and its ability to detect small artificial faults systematically seeded in our code. So we generate faults, we inject them in our code, and what we are expecting from our test suite to detect those codes. By doing that, we are measuring the quality of our test suite. Historically speaking, how we started by mutation testing. Actually, the idea came by a student named Richard Lipton in 1971. However, the first implementation was for a mutation testing tool was in 1980 and was part of a PhD work at Yale University. And as Olivier mentioned, having 100% code coverage doesn't necessarily mean that we are 100% sure that the test suite is covering all the hidden or the edge cases in our case. There is no unhidden bugs in our code. And that's lead us to answer, why do we need mutation testing? The first point is to measure the quality of our test suite beyond number of lines of code has been executed. And that will help us to improve our test suite, saying that there are some cases, edge cases are not covered by your test suite, and you need to cover them to add them to your test suite. Last but not least, mutation testing will help us by giving us some statistic and reports saying, pointing the time and the root cause of any regression in our test suite. And that's great. Now the question, how can really benefit and use mutation testing? Well, as I mentioned earlier, what we need to do is to create small artificial faults, inject them in our code. Those small faults, they will be injected once at a time. There will be one change at a time in our code. And we do that by creating a modified copy of our code. Each copy has only one modification at a time. Then we run the test, the relevant test against that code, and what we expect that the test suite should fail. That means the test suite was capable and able to detect the change, the modification. And in this case, we call that what we have created is that this small piece of modified code, we call it mutant. We're going to explain it in more details in the coming slides, that we managed to kill it. If the test suite passed, that means that our test suite is weak. It wasn't able to detect this change, and the mutant survived. I know that there are a lot of information here. Let's break them down into small blocks. So the first question, what's a mutant? A mutant is a modified copy of our program, one modification at a time. And then we run the relevant test against that modification. Let's have a look. Let's take an example. First of all, how many of you develop some Python? Okay, yeah. Not
How many in JavaScript?
Okay, that's great. All right, regardless of the programming language, the general idea is the same. So I have this piece of code, which is a method in Python that computes the square root of a number. So I check if the number is smaller than 0, then I raise an error. Otherwise, I retain the square root of that number. I write the unit test for that code, which is assert statement saying the square root of 49 is 7. If I run this test, everything will pass and everything's great. I'm going to create a mutant to make sure if my test is enough or not. So as I said, I need to make one change at a time. So here, the change I'm going to do is changing this operator. So I have the operator, the arithmetical operator, which is checking the number if the number is smaller than 0 to make it smaller or equal to 0. And then I will run the same exact test against this change. Remember, the goal is to check if the test, the relevant test, will detect the change or not. Actually, what will happen, the test will pass. And that totally makes sense, right? Because what I wrote in my test, okay, the square root of 49 is 7. So the test will pass and has nothing to do if I change this operator from smaller than to smaller than or equal 0. But in this case, so the test passed. In this case, the mutant survived. So the change survived because my test didn't detect the modification. And our goal is to kill that mutant. So how we do that? I go back to my test and I add extra statement, assert statement, saying, OK, the square root of 0 is 0. And now I rerun the test again, and as you can see, that the mutant has been killed, meaning that my test detects that there is modification and it fails. The test fails, means I killed the mutant, which is good. All right? Meaning that my test suite is effective, it's sufficient. I presented just one modification at a time, which was arithmetic operator. I changed it from smaller to smaller or equal. However, there are plenty of types of mutation and ways to create a mutants, and I let Olivier explain that.
Yeah, I broke it down to three main types. There's value mutations. Value mutations means we're going to create mutants by changing values, like a 0 become a 2, 5 becomes -1, big numbers become big numbers or small numbers, like a string becomes null. So we just change these values. So this is very simple mutant. Then we can have decision mutations. Decision mutations means we're going to change some statements like switch, if, else, and, or. We're going to change this. So and becomes or. The statement in a if is going to change. So these are more complex mutants. And then you have these statement mutations. These are even more complex mutants. Let's say we're going to change entire statement, like a function, maybe like removed, become empty, or just change the content of the function. I'll show you a few of them. Like for the arithmetic operator, for example, we can change plus to minus, times by divided, percentage, modulo, everything. So these are changed by the mutant in your code. You can have array declaration. So you can have an array that becomes empty array, or with more values in it. So this is done by the mutant. So you have your code, the array is changed to another one in your code. Not in the test, remember, in the code. You have assignment expressions, so plus equal become minus equal, all these very basic ones. So this can be also changed by the mutant. So block statement, here I have a function, say something, just a console log hello. And the mutant can just say, OK, let's remove the content of the function, run the test, and see if the test pass or not. You have Boolean, so true become false, equal become non-equal, these Boolean expressions. But you have many more. So you have conditional expression, equality operator, logical operator, string literals, object literals, optional chaining. So it also depends on your language. I know not every language has optional chaining, for example. So depending on your language, you have different tools. But you have all of these and many more. There's just a few more I want to show you because I find them quite interesting. You have method expressions. So in some languages, you have this embedded method in the language, like start with, that can be automatically changed to end with. Trim to uppercase becomes to lowercase. So depending on the language, you can have this mutation framework that change the embedded function. So this is very interesting. And last but not least, regex. I know that writing regex is quite complicated, at least for me. Debugging them is like nearly impossible for me. Writing tests for them is complicated. So the mutant will just change the regex for you. So this is very interesting to see if you wrote the regex and the test well, because it will change them and then run the test against them. So you may think at this point of the talk that, OK, so I wrote my code once, I wrote my test, and you're telling me that I have to write my code again like 1,000 times with all these mutants. So don't panic, there are tools for that. People thought about it. And for most of the languages, there are tools, frameworks, for creating mutants for you. And what these tools do is they give you a mutation score. So in a simple way, it's basically the number of mutants killed divided by the total number of mutants. It's a bit more complicated than that because you may have timeouts sometimes because the mutant just changed the while loop to like a true, and it just times out, or you can have some weird cases. But in a simple way, that's how you get your mutation score. And the goal, obviously, to have a 100% mutation score, because it means all your mutants have been killed. So that's, for example, an example you can have as an output. The mutation score is 50% because you have 4 mutants created, 2 of them have been killed, and 2 of them are still alive. And the goal, obviously, is to get 100% where all your mutants are killed. But I don't know if you followed everything, but I think a demo might be helpful at this point.
Yes.
Give a demo.
Yes, demo time. I think everybody's waiting for that magical moment, right? Sorry for the people who doesn't like Python, who don't like
There's a
Python.
JavaScript demo right after.
Yes. I don't know if they like JavaScript more even. All right. Okay.
You can see it. But that's awesome.
Sorry?
You can see it if you want.
No, it's fine. That's fine. You see well, right? I guess the screen is big enough. And okay. So our demo is really simple to illustrate the idea of mutation testing. So what I have here, it's a simple calculator. Okay. And with the simple basic functionalities, add, subtract, multiply, divide, and so on. And what I have done, I wrote a unit test for that code, as we can see here, for each function. And to verify that my code is passing and the unit test is passing, so I run the test, and we can see that I have all the test passes, all right? And if we want more, what we can do, since everybody loves code coverage, and I think this is the ultimate goal for everyone to really reach 100% code coverage. I can run the code coverage, and as you can see, I have 100%. But still the question, as Olivier stated at the beginning, 100% code coverage, I know for every developer, when you see 100% on your screen, oh my God, this is a magical moment, and everybody's happy, and life is perfect. But that's not necessarily mean that everything is fine and our test suite is perfect. So we will run the mutation test. And before showing you that, I listed a couple of tools. So here are the tools. You will see it for Python. There are tools Olivier will show us for JavaScript. And there are other tools for the other language. So don't panic. You will get to know the other tools for your favorite language, programming language. So for Python, there is a MutePy. The installation is pretty straightforward, pipe install. And here is the source code where you can find the development and all the comments about that tool. Small note, that tool doesn't work in Mac directly. It works in Linux. I tried it. So in Mac, what I do, actually, I run it in a Docker image, but the command is exactly the same. So the command is actually you are calling the script, MutePy, this script of Python. Here it is. And you need to pass few parameters. The first one, of course, is, let me make it bigger. Here. So what you need to pass, the target source, your source code, because the mutation needs the source code to make the modification on it, all right? And you need to pass the test. And here I'm passing the unit test, and then I will run it. Of course, there are other parameters, -m, to show all the mutants have been generated. And if I want to generate that report in a colorful way and in HTML format, I can also pass that parameter. So I run it. And as you can see in the screen, that there has been 14 mutants generated in total, and 9 of them got killed. However, there are 5 surviving. Okay, they're still there. And I have my mutation score, which is 64.3%. Okay, let's look into more details what those tests or mutants survive, meaning that my test actually is not covering some use cases. So if I go back from the beginning, so this one is killed, this one is killed, I can take this one. This one survived. Actually, here, the mutant, it's in green. So the initial code was for the multiplication function where I have the multiplication operator. The mutant has been generated by replacing this operator with another operator, the exponential operator, meaning that if I have in my test suite a case, which is actually this case, if I go back to the multiplication, it's here. I'm just trying multiply 2 and 2, and the result will be 4. So if I change the operator from multiplication to exponential, actually the test will pass because I will expect the 4, and the 4 is the correct answer. So in this case, the mutant survived, meaning my test suite is not enough. It's lacking some other use cases. And similarly for the other use cases. So I'm not going to go through all of them. But what I can do, I rewrite actually the test. So I rewrite it in another way. Or what I can do, actually, I can add extra case here, which is this one. Another assert statement where I try this, and the result will be 8. And we need to make sure the test pass. OK. Then if I go and run the mutation again, you should notice that there will be 4, because I managed to kill that one. And if I go back to all, it was the first mutant generated, we'll find it killed. So it was for the multiplication here. And as you can see, it's killed. How I killed it? I just modify my test suite. Meaning before it was lacking some use cases not covered by this test suite, and this test suite was not sufficient. OK, so this tool is really nice, and it generates some HTML report. So we can see the HTML report. Sorry, it's here, where actually it's different visualization of the result if you don't like looking at the command line. So it shows you exactly what I just explained, the score, the mutation score, and it lists you all, actually the mutant has been created. And in our case, we said there were 14. It tells you what's the type of those mutants. If you change constant, if you replace a constant with another number, if you insert another new statement, if you delete a statement, all those operators that, all those types that Olivier explained just a few minutes ago. And you can go into more details to better understand what's going on, what's happening. So this is the first tool. It was in Python. There is another tool. It's a mute. I played with it a little bit. Also, the installation is straightforward, and you can check it yourself using their website. The main difference between this tool and the MutePy, what I noticed, it generates actually less number of mutants. So here we saw that we managed to generate 14. There it will generate 8. In all cases, there are configurations that you can customize to say the percentage of mutant you want to generate and how you want to customize it. So that's doable. The last tool, I'm not going to spend a lot of time here. But what I noticed, this is pretty active, the community here. They are developing a lot and fixing bugs in this tool. And it's a muta test. And it's really dedicated for the Py test. What I showed you, it was for unit test.
There's 20 tools already.
No, for Python, that's all. No worries. And I think that's all for Python. And let's see the JavaScript one.
Yeah, let's go for JavaScript. So something that Maha didn't mention, that she showed that it's an HTML report, but most of the tools also generate other kind of reports. So you can have JSON or whatever that you can then use in your own tool report or CI/CD. These exist. So for JavaScript, I'm only going to show you one, which is Striker. It's pretty easy to install. It's an NPM package, and then you run Striker run. Just to show you the website somewhere here. Where is it? OK, here. So go to Striker. So Striker works for JavaScript. It also works for TypeScript, for .NET, for Scala. So you have Striker.NET, Striker for S, which is for Scala. And so what it does, it creates mutants, like Maha showed for Python. It supports all these kind of mutants, and you can see that depending on the language, not all the mutants are are available, because some of the languages are strongly typed, some don't have types. So it also depends, like I mentioned optional chaining earlier. So it also depends. And know that you can even, in the configuration file, decide which kind of mutator you want to create for your code and which one you don't want to create. So the documentation is pretty easy. So you have all these. So this is what I showed you before. Okay, nothing very new. You have a getting started, which is pretty straightforward, which shows you how to init a project, how to run your code. And a lot of things, your configuration file, you can decide if you want to have HTML reports, you want to know the code coverage analysis, all the mutants you want to create. You also have a dashboard. They have a SaaS tool, so you want to generate a dashboard on their website. But let's go in VS Code. So here I have a kind of the same thing Maha did. So I have a very simple calculator, which doesn't, even the code doesn't cover all the cases, but I have a very simple one, and I have my test suite here. So same as Maha, I can run my test. So I have a package.json here. So I'm using jest. So if I come on. So I can run my test, and what it does, it even tells me the code coverage. So you can see that as Maha, I have 100% test coverage, 100% of the functions, not of the lines. Okay. But anyway, I have a test suite, everything passes, the six tests pass. But then if I want to run Striker, so I run Striker, it's going to create mutants here. And you can see that I have 40 mutants created, 2 survived. And I can go see the report somewhere here. I'm lost in the pages. So here, I can see the report. So this is my calculator. So I have 77% of mutation score. I can go here, and this is my file. And you can see that here there's an issue. So he created some mutants. So that one, it replaces like less than 0 to less or equal to 0. There is another one where it just replaces it by false. So these don't pass because it tried these changes. I can also have the output in the console here, like Maha showed, but so there is here. I can see what it did. So basically what I have to do is just to I just have to create new test. So I create a test where I had to do a square root of 0, just to make sure it's 0. And if I run the test again, Striker, you will see that I only have normally one mutant that survived. And if I go back, the right side here, if I go back here, you can see that there's only one created that doesn't pass, which is the one when it raises the error, which I can also fix very easily. I just create a new test. Say if I have -1, I expect it to throw the error number should be positive. And then if I run my test, you can see that I have 100% test coverage, and 100% of my 100% score, sorry, and 100% of my mutants were killed, which is what I'm looking for. So again, doesn't mean my test or my code is wrong. It means that I didn't have enough tests before to test everything. So this is a very simple project. I want to show the one that comes with so there is a demo on Striker, so you can clone it on a repo. So it's a more advanced website. I think it's in Angular, if I remember well. And so I can run my test. And here you have way more files and way more functions. So you can see that here I have all my functions and all my lines covered. So I have 100% perfect test coverage. But now if I run Striker, oops, I won't do it. Come on.
You put the space.
Yes. So I run Striker here. So it will generate a report like it did before. So you see it creates like 100 259 mutants this time, which is way more. You can see the result here, but I can also see it in here. So here is the mutation score I have, which is actually pretty low. And you can see, you can go see for every file, like on this one. So, and you can see what it did, the same thing that happened before. So you can see that here, it just removed the entire content of the function. Here, it just replaced by undefined. So here you see that even though that's a pretty big project, and even though I had 100% test coverage, my mutation score is very low because there's a lot of edge cases that aren't tested in my test suite. So that is all for JavaScript. And back to you.
Thank you. So we showed you two examples, two demos, one in Python, one in JavaScript. And we showed you how can we use the existing tools to implement mutation test. I want to recall that code coverage metric is a very great metric to have, and having 100% code coverage is nice, and it's a good indicator to check our test suite. But again, this is not enough. It doesn't tell us if our test suite is sufficient and effective and all the hidden edge cases, all the bugs are detected. And that's why we need a complementary metric named the mutation score. And our goal is really to get high mutation score. Of course, the 100% is perfect, but I will show you later, sometimes getting 100% also is difficult. Why we care about all this? Because the test suite is our primary source of truth to say that our code is meeting the standards and supposed to do what, and it's doing what's supposed to do. And to guarantee that, we want to we write tests for that, and we want to guarantee that this test we wrote is sufficient. So as I mentioned, having 100% code coverage is great. Trying to reach 100% mutation score is great, but sometimes you reach 99 and you keep asking yourself, why I'm not getting 100%? Well, actually, there is a reason, and this is fine. The reason behind that, actually, there are kind of mutants they name equivalent mutants. What does that mean? So those equivalent mutants, they are also changed in the copy, a copy of our code. We make small modification, one modification at the time. But actually, they are not changing the logic of our original code, meaning that if I add them, create them, the test will pass, those mutants will never get killed. Let's see an example. So here it's again piece of code in Python, but forget about the programming language. What I want to do is I want actually to get an URL, then I want to get this web page by giving URL, okay? So as optimization, I say, okay, let's implement a cache using a Python dictionary where the key of this dictionary, the URL. So the first time I get this URL, I will fetch the page, the web page of this URL. Then I will save it for the next time. Next time I get the same URL, I don't go to the server. I just get it locally because I saved it just in the dictionary. So having this, it's really optimization thing, right? I'm improving the quality of the performance of my code. A mutant for this code, which will not be killed, if I remove the whole if statement. So imagine that I remove the whole if statement, meaning the code will work, right? But every time I get the URL, I will every time go to fetch the page from the server. So what I did, actually, I just removed the performance part. So the mutant will never get killed. And this is fine. And that's what we call equivalent to mutant. And in this case, you will never reach the 100% of mutation score. OK, we saw all the advantages of mutation testing, and it seems a great tool. However, there is nothing perfect in life, so it has some limitations. The first one, I think you already saw that it might be time-consuming and very expensive because we have like thousands of mutants can be generated, and then we need to test all of them, run the test against all of them. So this can be really exhaustive, and that's why we have those tools that they help us in automating all this process, which is great. But you might ask yourself a question. Like what we showed you, it was small example calculator. How can we use mutation tests at scale? And this is really great question to answer. And here, thanks to Google and their paper, actually they have done a practical study about applying mutation tests on their code base, which is 2 billion lines of code with 150 million test suite running on daily basis. I'll let you imagine how many mutants can be generated out of that code for that test suite. It's huge, it's large. So how can we really run a mutation test in this case? It will be time-consuming and really overwhelming to the developers. So what they propose in their paper, that we should actually, first of all, we should apply the mutation testing incrementally, meaning just in the new added code, so we don't run it in all the code base we have. And we limit it to the code review process when you have a PR per request, so you run the mutation test. You need to filter the mutants. So there are mutants that are irrelevant, and it seems to the developers they are irrelevant, and they will not impact the code. You need to remove those equivalent mutants, because those, they have impact on the performance. They will not be killed, so we don't need to run them. You need to filter also more mutants and limit number of mutants created per each line of code, per each statement. And this will be applied for the new added code. And by this, actually, they managed to use mutation testing in this huge code bases, as I said, using their recommendation. Last limitation, I think we all agree, mutation test needs the source code, so it cannot be applied for black box testing, because you need to make the modification in the original code to be able to use the mutation test and run it against your test suite. Well, I guess we reached the end of our talk. So as takeaway, remember that having 100% code coverage is great, but can be misleading, because there will be many use cases hidden. And that's why we would like to have another metric, what we call as the mutation score, because we care about the quality of the code rather than the quantity. Generating and using mutation tests can be overwhelming, so that's why we need those tools, and we need to automate everything and to automate the whole process. Last but not least, as I mentioned, also getting 100% of mutation score can be difficult, and that's fine. You should accept that fact. As we promised, not only for Python and JavaScript, so for those people they prefer other languages, so we have other mutation testing tools. So for example, for Java, it's very well-known one, PyTest, and it's really used everywhere. Even they have a plugin on SonarQube. So this is really, the topic is getting like super hot, and everybody want to use that. For C and C++, there is Mule. There is for PHP, Ruby. I'm not gonna go through all the list, but as you can see that for each programming language, you have the mutation testing tool that you can use it. So you don't need to do that yourself. Here's a list of references we have used to prepare this talk, and
we'll share the slide on Twitter if you want to take the
yes,
links.
or you can find them actually in slides.com and my account. And thank you very much for your attention being here. I hope everyone will use mutation testing, try it, apply it in your team, in your project, and share the result with us. Thank you very much, everyone.
Thank you. And we have time for questions. Yes.
In our current code base, we go for code coverage about 85%. Is this still valuable, or do you need to go to 100% coverage first before you start this?
The question is that Just repeating for people. So you have a 85% of test coverage, for example, in your code. Is it still relevant to run the mutation test, right? It is possible. I mean, on my example, I had 88% of test coverage, and I can still manage to run the mutation testing. So, yeah, there are two different kind of tests, and you don't have to have 100% of the first one to do the second one.
Yeah, it's irrelevant. But actually, the question you should ask yourself, why do I have 85%? What's preventing me from getting the 100%? Yeah. Okay, I got it. But yeah, that's completely true. But running a mutation testing has nothing to do with the code coverage being 100%. Exactly. You can run it separately.
And it will basically test your test. So you will have less mutants that have been killed, but it's relevant. At least you can test your 85% of test.
Yes.
Welcome. Is there any other question? People are either waiting for the next session or sleeping.
Yeah.
Yes. I think Striker works with TypeScript. I'm almost pretty sure. Let me check. Yep. Yes, it works. And Maha mentioned something earlier, which I don't know where it is, but
How about SonarCube?
yeah,
That's here.
integration.
Yeah.
No, it's not here. There is a web page here that shows you all the integration with the different CI/CDs and what you can do with it. Don't remember where it is. That's the dashboard for report. Here you can see, the CI/CD you can use with Striker, and there's something with StarCube somewhere. Don't know where it is.
Other questions?
Yeah.
I found that by testing, for example, the message, the reason why the mutant survives is not really explicit most of the time. In case your mutation score is really high, and why the remaining survive, and
Yeah.
not explicit. And which one?
Yeah, you're saying that. So what you're saying is that it's not explicit. Sometimes your mutant survives, but you don't know why.
Yeah.
Okay, the only thing you see is the change that has been done. It doesn't tell you what kind of new test you have to write.
Yeah, it doesn't give you recommendation. Yes, that's too bad. Yeah, but probably the one at SonarCube, this plugin, I haven't tested it yet. Actually, it's my to-do list to check it. If it gives some recommendation, so it might gives you. I haven't tested yet.
We tried it in our company, but
Yeah.
most of the time the proposition is not valid. So
Okay.
not even accurate. Sometimes
Apparently, still we need AI.
I know that Semantic is working on it. But
If you were in the keynote, apparently there's some very nice AI tools to generate tests. That's what he showed during the keynote. So very interesting, right?
I have a question. Is the list of mutants constant, or it's a new one that is generated each time you run the program detection?
No, it's constant. Yeah, it's constant. Yeah, but so the question is if the list of a mutant generated it's constant, or every time I rerun the mutation test tool, it will generate a new mutant. No, it's constant. However, as we mentioned, that there is a configuration file where you can limit the number of a mutant and check what operator you want to generate a mutant for. Yeah, but it's constant. Yes. Yeah.
Thank you.
You're welcome.
Okay.
Other questions? Probably we need to ask if everything is fine there.
Hello, is there any question over here? You're good? Okay, perfect. Thank you.
All right. If there are no more questions, thank you very much, everyone, again. and see you soon.
Thank you.
Thanks.